The topic of this lesson is rational exponents, also referred to as fractional exponents. You can see the first objective, we're actually going to clarify how absolute values are used with radicals first, and then we're going to get into the rational exponent stuff, where we're going to simplify them and also factor some expressions that have rational exponents in them. So the first thing is when you think about whether or not you need absolute value. It's kind of a two-step process. So the first thing you want to think about is the domain, right? So if the domain contains negative numbers, then you have to go to the second step. If not, you're done. You don't even have to worry about absolute value because you know you can end up with a negative. So for instance, if you look at this example here, because the domain is just all positives, or we'll say 0 and greater, right? So the domain is from 0, sorry, we can include it, 0 to infinity. We don't have to worry about getting a negative number. And the reason we can't get a negative number is because of the root x, right? So it's just not in a domain. So we don't have to use an absolute value in this instance. When we do have a domain of all real numbers, then the next question we ask ourselves is it okay for the variable to have a negative value? So for instance, if you look at the cube root of x cubed, it's okay if the variable is negative because the cube root of a negative is negative, right? And so we end up with a negative value. Likewise, in the x to the fourth example, notice that if x is negative, we're going to square it and it's going to become positive anyway. So there's no need for the absolute value there. Here's an example of where we do need the absolute value because, for instance, let's take x is negative 4. So the square root of negative 4 squared is 4. Notice it's not negative 4. So basically what we have to do is we use the absolute value there. So let's practice some of these. So basically just ask yourself in each of these instances, do you need to use the absolute value? All right, so again, go through the two-step process. First consider the domain, and then from there decide if it's okay for the variable to have a negative value. So looking at this first one, we do not need an absolute value. So this is just x, again, because we have the odd root. In this one, we do need an absolute value. In this one, notice that the domain is just 0 to infinity because of that fourth root of x, right? X cannot be a negative number. So even though when we multiply these together, we get the fourth root of x to the fourth, we still do not need an absolute value because x cannot be negative. It's not in the domain. On the contrary, because this is all reals as the domain, so x can be positive or negative or 0, when we get the fourth root of x to the fourth, we then have to use the absolute value. And here, again, think about the domain. So essentially, we have the sixth root. So if x were negative in this instance, we would end up with the sixth root of a negative number. So here the domain is just 0 to infinity, so we don't have to worry about negative numbers. So we would just get x, sixth root of x, instead of the absolute value of x times the sixth root of x. All right, so I hope that clarified some things about when and when not to use absolute value in terms of radicals. So let's get on with the rational exponents. So think about these two expressions and whether or not you know what they mean. So pause the video, see if you can figure it out. So 4 to the 1/2, if we want to, let's look at it this way. What if I were to square it? Right, so I know that when I raise it to a power, I multiply the exponents. So that's just going to give me 4 to the first power, also known as 4. So if I unsquare that, right, then basically I'm going to get 2. So 4 to the 1/2 is 2. So it looks like the 1/2 might be the square root, right? The 1/2 power might be the square root. Let's see if that holds for the 27. So if I cube this, then that just gives me 27, right? Now if I uncube it, we know that that's going to give us 3. So it looks like 27 to the 1/3 is 3, also known as the cube root. And it turns out that whenever you have a real number raised to 1 over an integer, then it's simply that root. So anything raised, so let's see, a to the 1/7 would be the 7th root of a. Now, what if we've got a numerator that's other than 1? What do you think these would be? Again, pause the video and see if you could figure them out. So looking at 81 to the 3/4, we could rewrite that as 81 to the 1/4 raised to the 3rd power. Because again, if we multiply those exponents, we get 3/4, right, as the new exponent. And 81 to the 1/4, we just learned above, is the 4th root of 81, which is 3. So this just becomes 3 cubed, which is 27. The negative exponent, that just means we're going to put it in the denominator as a positive exponent. And just like the previous example, we could think of this as 1 over 8 to the 1/3 squared. And 8 to the 1/3 is 2. 2 squared is 4. So this is actually 1/4. So here's what we got. Again, a real number, and now we have m and n that are integers, right? Greater than or equal to 2. You can think of it in two ways. You can basically leave the numerator as the exponent, as we're doing here, right? And then raise that to the fraction, which would get you the nth root of a to the m. Or you could raise to the fraction and then raise that to the numerator. And notice that you get the nth root of a, all of that raised to the m. So which of these two do you think is better, if either? So give that a thought for a moment, and then I will reveal what I think. And maybe you guessed it. It's better to do the radical first, and then the power second. And the reason is, by doing the radical first, you end up with a smaller number that you're going to then raise to the power. So for instance, if we go back to this example up here, 81 to the 3/4, I'm not going to take 81 and raise it to the 3rd power first and then find the 4th root, because that's just crazy talk, right? 81 times 81 times 81 and then take the 4th root of that. So much easier to take the 4th root of 81 first and then cube it. So there's that little note. All right, let's get into factoring now. So remember that when we're factoring, we take out common factors, and we want to use the exponent that is the least. So in this example here, we're going to take out a 2x to the 1/3, because 1/3 is less than 4/3. And what I'm going to be left with is a 2 times a 2x plus 1 plus a 2x. Now how did I get 2x? Well, remember that when we're factoring out, we're going to subtract exponents. So 4/3 minus 1/3 gives me 3/3, which is 1. So I basically get x to the 1. But what I neglected is that I took out the 2 already. So it is just an x in there. So let's scoot that over. And now I just simplify what's in there. So it's 2x to the 1/3 times, that's 4x plus 2, so 5x plus 2. Here we have another expression. Essentially just a binomial, right? I have one term here and one term here. They have a 2x in common, so I'm going to pull that out. They also have a 3x plus 4 in common. And as in the previous example, I'm going to use the smallest exponent. So I'll use 1/2, because 1/2 is smaller than 3/2. And so what is left here? Well, the 2x is gone from the first term. And then 3/2 minus 1/2 is 2/2. So I just get 3x plus 4 to the first. And then a plus, so I have a 2x left here. and I factored out the 3x plus 4 to the 1/2, so that's all I have left there. So the final factored form, simplify what's in there, looks like 5x plus 4. And there you have it, factored. The same holds true with negative exponents. We want to factor out the least. So I can see that there's a 4 in common, and I'm going to factor out x to the negative 3/4, because negative 3/4 is less than 1/4. So what am I left with here? I'm left with a 2. Now 1/4 minus negative 3/4, that is essentially 4/4, leaving me with x to the first minus 1, because I had factored out 4x to the negative 3/4. So there it is, factored. And lastly, I see there's a common factor of x minus 1. And again, using the least exponent, I'm going to factor out to the negative 4/3. And what I'm left with is a 1 plus, and then negative 1/3 minus negative 4/3. That's negative 1/3 plus 4/3, which is 3/3. So I just get an x minus 1 to the first. So now I have x minus 1 to the negative 4/3 times x. Now technically I should move that down to the denominator so that we have positive exponents, and I need to go back and do that to the other problem as well. So back in number 3, what we need to do is we're going to leave the 4 up top with the 2x plus 1, or sorry, the 2x minus 1, and then put that over x to the 3/4. So that's the factored answer. All right, so again, with negative exponents, we don't want to leave them in the final results. All right, so that's factoring. Just remember to pull out what's in common and use the lowest exponent. Thanks for watching.